Hello, good evening, good day, good morning, wherever you are in the world. Yes, Arya, I see you in the chat. And yes, subatomic particles. All right. Okay, so for this, I just want to clarify what's happening here. Um, I don't have a student right now. This is like a special stream because some of the grade 12 students that I have, um, they're requesting a particular lesson on something. So I want to start off. That something is Feynman diagrams, by the way. Okay. I want to start off first with saying how it came about, real quick, because we still need to learn a little bit of the history here. The history is basically part of the knowing how science basically corrects itself. Okay, and that's the thing about science. Science is one of those fields that can correct itself. Science is not absolute, and this is one misconception that a lot of people seem to have. Okay, this is a really common misconception. Science is not a body of facts. Science is a process of knowing, unknowing, re-knowing. Okay, um that's why the important thing inside the important thing we're teaching in class is not just the facts, because the facts can change. Okay, instead we're not focusing only on the facts, we're focusing on the skills of how to do science. So anyway, like I said, we're gonna do all right, so this is our topic for today, and I'm gonna try a different pen. I'm gonna try the highlighter in Jamboard. By the way, for those who are not aware, I use Jamboard as my board here. It's a really easy board to use compared to the other online boards I've seen. Okay, and I like using online boards because it's also easier to share this with anyone who wants to have a copy of those Jamboards. Okay, so this particular Jamboard, I'm gonna make this available for everyone to view. Okay. All right, so going back, so let's take a look at subatomic particles first. So let's start with that again. What we already know about subatomic particles. Okay, what we already know is we have protons, electrons, and neutrons, right? Um, okay, let me just get to that particular thing. Okay, I'm getting a lot of images online just to make this a bit easier. So again, I'm gonna credit the sources later because there's a lot of them here. Okay, so I'll credit the sources in the description later once I've updated everything. But anyway, um, for these sources, thank you. Now, if you feel like I should not have used your source later on, if anyone's listening, then feel free to contact me, and of course, I will change stuff. Okay, but I guess I'll use Wikipedia because Wikipedia is always a free source. All right, I'll just get those Wikipedia things. Okay, so we know that the simplest possible thing we know about atoms, well, not the simplest, but the most basic. Okay, it is from Wikipedia, so I don't think there's gonna be any issues here. And okay, there we go. We know that an atom is composed. It's still copying and pasting here. That the atom is composed of, let's say that these are the protons. Actually, no, those should be the neutrons by color. All right, so that's neutron. How do I know? I just want to make it like that. So those are the neutrons. These would be the protons. For those who are on the stream, if you wanna, well, I just wanna ask you, does this pen look better to you compared to the previous pens? Okay, so anyway, so these would be the electrons. Okay. All right, for the longest time, well, not really long, when we discovered protons and electrons, we didn't discover the neutron like until a few years after we discovered the proton. Okay, but the thing here is, once we discovered all of these things, scientists kind of thought, what would happen if the protons collide with protons? Okay, protons collide. I'll just say P here. Neutron for use N, and then for electron we'll use E. Okay, what if the protons collide with another proton? Okay, think of now in that particular case, the idea is, well, let's see what happens. So they have these things called particle accelerators. Okay, Arya, not really. Protons don't really touch each other in the nucleus, which we will get to later. Okay, we'll get to that later. All right, so anyway, oh, by the way, Arya, since you're there, I want to ask you, is this pen better? What do you think compared to, let's just say, this pen? Just gonna say hello here. Which pen is better for you? Which one can you see more easily? Can you read more easily? Okay, so while I'm waiting for your response, I'll keep with that. This pen. Okay. All right. So anyway, here's the problem. At this time, there was a time wherein we thought that we knew everything. We knew that the proton was the smallest positively charged particle. Okay, so you prefer this pen. I just want to make sure you prefer this pen, right? Or the one I said hello. Oh, the one, it's this pen then. All right. Okay, so anyway, since you prefer that, I'm going to go back to that pen. Okay, so anyway, where was I? There was a time, I won't go through the details of the years and everything. You can do that yourself when you actually read your books, for those who are in grade 12. But it's never tested. Those years are never tested. Okay, hi Joven. You prefer the second pen as well, right? Okay. All right, so anyway, the idea here is there was a time wherein we kind of thought that the proton was the most basic positive charge, the neutron was the most basic neutral charge, and then the electron was the most basic of negative charges, which makes sense according to what you learned, right? But the point here is, so what would happen if you smash a proton with a proton? You would expect nothing to happen. Maybe they'd bounce off each other and whatever. Okay, no worries, Arya. Just sleep whenever you can. But anyway, this is just gonna be a short one. Anyway, the idea here is, when we had a proton here and we had a proton here, and this was sent to collide with the other proton. Okay, something weird happened. Okay, of course, energy got produced and everything, but again, you would expect this. So the expectation was what? The expectation was the protons would basically destroy each other and produce energy, and maybe a few other particles, right? The expectation was energy. Hold on, I gotta refresh the board. It's a bit weird right now. Just and that's weird. There. Okay. Okay. Energy is gonna be produced, and basically there's gonna be an explosion. Okay. Okay. So there's that explosion, and then some particles will be produced, right? Plus particles. Okay. And what just happened? Okay, hold on. I think I accidentally clicked on my board. Clicked back on the browser. Hold on. All right. So anyway, and here's the thing about these particles that were expected to be produced. Scientists, the physicists at the time, kind of thought that these particles would be of a set answer, basically. Okay, you would not, they would always get the same particles. That's what I meant. Okay, so same, always same particles, right? Okay, that is as long as the collision happens with a certain amount of energy. Of course, if you change the energy, you would expect something else, right? But the expectation was no matter what level of energy they would do, even if they had different kinds of energies in there, they would always, the observation was, okay, the observation was, of course, the energy still produced. Okay, however, the particles are also produced, but there are always new particles being produced. Well, at least when they started out with it. Okay, so it's just like this, basically. Let's imagine you're throwing a stone onto a stone. This is gonna be the analogy here. If you throw a stone onto a stone, you would expect sand. You would expect the stones to like destroy each other, and then you'd get some smaller grains of sand, right? That's the expectation. The observation was when the stones hit each other, sometimes you get sand, sometimes you get pebbles, sometimes you get, let's say, dust, different kinds of particles, and sometimes you get something totally unexpected. Let's say you get like a flower. Yeah, something like that. So that's the idea. Okay, so you may be wondering, what do I mean by that? Well, the physicists at that time basically called it a particle zoo. So in other words, all the particles discovered were put in a particle zoo. Now, why do we call it a zoo? Okay, we call it the zoo because if you go to an actual zoo, you don't really see one kind of animal. You don't see like 5 kinds of animals. You don't see 10 kinds of animals. You see several, like at least 50 kinds of animals, right? Specifically, when physicists got here and they started doing these experiments, they get more than 100 particles. More than 100 types, okay? You see a problem. If you keep smashing protons and protons together, but you keep getting different results, 100 types of results, there's something wrong with what you know, right? Okay. However, there's this one physicist. His name was Murray Gell-Mann. Okay. And he proposed a very simple solution. What if these particles were not the elementary particles? They were not the basic particles. What if these particles were not elementary, right? In other words, there's still a few smaller particles, even smaller than what we know. Okay, so with this particular thing, he came up with the idea of, you may have heard of this word, quarks. Okay, quarks. That's the idea he came up with. He didn't come up with the name quark. Somebody else did. I think this was, if I'm not mistaken, this happened in 1960s. In the 1960s. So not that long ago. Right? So anyway, what are quarks? Now, I'm just gonna go straight to the point on this next one. Okay, so the idea of quarks is that right now, and this time I'm gonna go again to the internet here. Okay, so Wikipedia, thank you. Yeah, this is gonna work. Right? Image, and according to Wikipedia, again, I'm just copying this from there because this is the same thing that we learn wherever. Okay, right now, this is what we call the standard model of our elementary particles. Okay, bye-bye, Arya. I'll see you. Okay, if you want to keep watching, you can watch later. Thank you. See you. Good night to you. All right, so this is what's called the standard model. And again, you will notice that they are 1, 2, 3. Well, 3. I'm going to erase this bit. Okay, there are 3 main kinds of particles here. We're going to focus on this bit for today. On this bit. The quarks. Okay, now what do we see here? Okay, these quarks, the way we understand them now, there are 6 types of quarks. Okay, now for us, the most important thing for IB physics, and I'm going to focus on that, okay, are these 3 quarks. These are the important ones for IB physics, but the rest are important for the rest of particle physics. Okay, now, so as we see here, there are 6 kinds of quarks, but I'll just describe what the up, down. Sorry, I should have said down. I made a mistake here. Sorry, that should be down. So let's do that again. So up, down, and strange. So these 3, not the charm. Okay. The up quark has a charge of positive 2/3 of the electron. Okay. The down quark, the charge is negative 1/3 of the electron. And finally, the strange quark also has a charge of 1/3 of an electron, also negative, but it has a property called strangeness. The strangeness, everything else equals -1. Everything else, every other quark has a strangeness of 0. But the strange quark has a strangeness of 1. This will become useful later on, but for now, I just want to say it out now. But we're going to focus again for now on these 2, the up and down. Okay. So what else do we know now? The proton is actually composed of up, up, and down. Up, up, and down. Which makes sense because if this is 2/3 of an electron, the charge here is 2/3 of an electron. So you add that, and then you subtract 1/3. That's gonna give you exactly exactly the charge of the electron, but it's positive. Same thing with the neutron. The neutron is actually up, down, down, and that makes sense again because this is 2/3 minus 1/3 and minus 1/3. If you add those up, the charge will be equal to 0. The neutral, they're neutral, right? So what does this accomplish? Having quarks, okay, and I'll type this in here. I will not do anything else. So having quarks erases the particle zoo. No, not erases, simplifies the particle zoo. Okay, how does that happen? Simply because, oops, I'm on the wrong window. Hold on. Having quarks simplifies the particle zoo for one reason, because it just basically says that all those particles in the zoo, all those new particles in the zoo are just combinations of quarks. Okay, right. So, the rest of quarks, we'll go through them later because again, our focus for today is not really this, but this is a useful idea to bounce off the next thing. Okay, the next thing here is let's take a look at a particular thing. Okay, now we go back to the standard model. I want to focus on this now, on the leptons. Just these. Okay, now these leptons are basically, again, just electrons. Just think of them as electrons. Electrons are the normal electrons. Muons are for lack of a better word, fat electrons, and tau, they're obese electrons. That's the way I think about it, because the only thing different between the electron, the muon, and the tau are, there are two things different. One is their mass, and the other one is how stable they are. Electrons are stable, muons and taus are not. Okay. Now, what do I mean by that? So let's focus on the muon. Okay, so the muon is a particle called a lepton, as we see in the thing. Okay. We'll go through them later. We'll go again through how to remember these later, but we'll focus on this idea about muons. Okay. The important thing here about muons that I want to go through is that because they are heavier than electrons, they are unstable and therefore they decay. And muons decay in many different ways. Okay, so that's our focus for today. Decay in many possible ways. Okay, now I want to show you one thing before we go there. Where is that thing? Okay, here it is. I'm going to show you an equation. You don't need to totally understand this equation, because my point is you shouldn't understand this equation. All right, but anyway, having said that, okay, so the next thing we're going to go, again, we're going to put everything together in a while. Okay, the next thing here is this equation. I'll be honest with you. The last time I worked with these equations is when I was in university. So I've pretty much forgotten how to do this. But anyway, the idea here is this equation is really hard to, it looks hard, right? It looks hard because it is hard. Okay, this is called the Schrödinger equation. Okay, and the Schrödinger equation is basically the equation that describes everything within quantum physics. Now, imagine this. If you're having a hard time comprehending what this means, you're not alone, like I said, right? Everybody has a hard time with this. In fact, physicists had a hard time with this. To be specific, in the 1950s, had a hard time with this, yeah? All they did at that time, of course, computers were still pretty big, calculators were not common, so the math they would do was all by hand, right? So basically, it was not only by hand, but look at this equation. Basically, physicists in the 1950s had a very hard time, right, working with this formula. For us now, it's easier because of computers and everything. But anyway, I'm gonna go to my point. So imagine this. So the point here is, how does that connect to muons? Okay, so if muons can decay, let's just say muons, there are so many ways can decay. Let's say in this mode, 1 mode, 2 modes, 3, 4, 5, etc. Okay, so that means in several ways. Okay, so because muons can decay in several ways, imagine using the equation once here. Use equation here to describe this decay. You use the equation here again. And so on, so on, so on, so on, so on. So you can just imagine how hard it was, right? And that makes it very hard to predict how muons actually decay. Then, somebody thought there must be a better way, right? There must be a better way. We can't just keep using equations and everything. So even physicists, the ones you think are smart people, they don't like working with math. So just so we're clear, okay? Professional scientists, physicists don't like working with math, but they have to do it, so they get good at it, okay? The point here is, let's go back. Richard Feynman, okay? This physicist came up with a manner to, instead of calculating these things, he came up with what we now call Feynman diagrams. Okay, now Feynman diagrams are basically, this is a tool. Okay, this is a tool to see which possible decay modes, possible interactions, let's use the word interactions, in the quantum fields, quantum realm, are more likely. Okay, so this allowed, it didn't make the calculations easier, but this allowed physicists to focus on which ones to look for. Okay, physicists to focus their efforts on the more likely scenarios. Okay, so again, this is the importance of the Feynman diagram. Okay, now this is what I think the students are waiting for. What exactly are they and how to use them? Okay, so the Feynman diagram is basically something like this. I'm gonna copy one from Wikipedia again, but I'm not going to solve that. Okay, okay. Yeah, this is a possible way of doing it. Okay, so again, this is an example of a Feynman diagram. This is not the only Feynman diagram there is, but this is one of those examples. Okay, you will notice three things. Okay, now there are rules for Feynman diagrams. Again, grade 12 students, if you're listening, this is, again, you've learned this before, but we'll go through this again. Okay, so the first rule is there must be a junction somewhere. Okay, and I'm marking those as junctions. Okay, there must be junctions somewhere, right? Now, what do these junctions do? These junctions represent interactions. Okay, now at each junction, okay, so anyway, while I'm doing this, so these are the rules only, but what these, again, for those who know it, you know what to do, but for those who are new to this, these rules arise from the fact that quantum mechanical interactions always lead somewhere. Okay, now at each junction, there must be an arrow in, there must be an arrow out, and there must be a non-arrow. Okay, for our purposes, this is usually a wiggly line. There are other types of non-arrows we can use, but for now, we'll use wiggly lines. Okay, so let's take a look at this example. Let's take a look at the rules on this example. So here's a junction. There's a junction right there. The junction has this arrow coming in, this arrow coming out, and that wiggly line right there. Okay, that follows the rules, right? This junction, again, has the same thing. It has an arrow coming in, it has an arrow coming out, there's a wiggly line. Simple enough, right? This simplicity of the Feynman diagrams makes it easy to see which interactions are more likely. Because think about it this way before we move on. What's going to be more like a more likely interaction? A simple diagram or a complicated diagram? Simple diagrams would be easier to do and therefore are more likely to happen. Okay. Now, there are other rules which we will go to later on the next slide. Okay. I'm going to copy. Okay, I'll get that same diagram. Okay. I think I'll get that same diagram. Okay, here's the idea. Now, what is rule number 3? Okay, rule number 3. Okay, you must select a time direction which is either up or right. Okay, now I want to make sure again that we know what's happening here. Up is the standard way of doing it, but right is the IB way of doing it, and for us, we'll follow the IB way. Okay, so in other words, time goes this way. Okay, in other words, what is happening here? This electron is moving through time, which means this is an earlier version of the electron. This is the present version of the electron. Same thing with this electron and this electron. This is an early version. This is the now or the future version. Okay, so time goes like this. So again, focus on the fact that in IB, most of the time arrow goes to the right. Now, make sure that you also are aware that it can go up, because sometimes they do make it go up. Okay, so that's rule number 3. What is rule number 4? Rule 4. Okay, an arrow in the same direction as time okay, means it's a matter particle. It doesn't mean before that, let's go here. An arrow going in the opposite direction, arrow opposite time, is antimatter. Okay, what does this mean? It doesn't mean that the antimatter goes backward in time. No. Okay, it simply means that you have an antimatter particle and you have a matter particle. You still follow the time arrow itself. Okay, so all right, so let's take a look here. In this diagram, this is an electron. This is a normal electron. This is matter. Why? Because it's pointing to the right. This thing is also a normal electron because it's pointing to the right. And so is this, and so is this. Don't mind the up or down directions in the pointing. Just go to the general thing. Is it up? Is it going to the right or is it going to the left? Okay. Here's another example, this time of Feynman diagram with image. So here's another example. In this case, let's see, is rule 1 followed? Yes, rule 1 is followed here. Okay, because let's take a look again. Junction here, in, out, wiggly line, check. Right? Same thing here. In, out, wiggly line, check. So rule 1 is followed. Okay. The next rule we need to actually follow, that's rule 1 and 2, by the way. Rule 3 and rule 4 go together. Rule 1 and 2, check. Okay. Rule 3 and 4. Why did it go back there? Rule 3 and 4 is time arrow. Again, you must draw your time arrow. Let's say that's a time arrow. Okay. What does this mean? This is a going to the right. So matter. This is matter. This is also going to the right. So matter. Okay. Let's use blue on this one. This is going to the left. So going to the left. So this is antimatter. And finally, this is also going to the left. This is also antimatter. Okay. What does this mean? I'll just put the interpretation of this diagram. So this diagram means that an electron and an anti-electron. I'm just going to use the word anti-electron first. That's how you describe antimatter. Okay. Usually you just put the word anti in front of the matter particle. So there's this electron and the anti-electron. They meet up. Produce a photon, and then separate. Okay, not actually. Produce a photon. Okay, then the photon separates into the electron and anti-electron. Okay. Just keep it simple. Whatever you see, you don't need to actually say anything complicated here. So rule 3-4 is again checked. So again, this is what this diagram means. You rotate the problem, it changes the problem. It changes the situation. So here's an example. Okay, done. I'm literally just gonna rotate it like that. So you see, it's the exact same problem, but I'm rotating it. This now changes everything because you still have the time arrow going to the right, right? So time still goes this way. What does this mean? Okay, this is a little bit different because of the fact that, okay, I think I'll rotate it a little bit more. Just like that. There we go, like that. Okay, so what does this mean here? If time goes to the right like this, this means okay, this means the electron on the top emits a photon, the wiggly line. Okay, and changes course. Okay, all right, and then the photon then strikes a second electron, which is the one at the bottom, and it is absorbed. The second electron, what does it do here? The second electron, sorry, it's not an electron. This is a strikes an anti-electron. Okay, there we go, and then it's absorbed. The second anti-electron is deflected. All right, so this is what this Feynman diagram means. So you see, you can have, this is an example of, you can have different interactions by changing the diagrams, and these are both likely because they're simple diagrams. But if you have a more complicated Feynman diagram, it's less likely to happen. So for example, I'm just gonna give you one that still could happen, but it's not as often as that. Okay, so let's say you have this. This is your electron. This is your electron. Then it emits that. And then this photon does this. Okay. And let's say that's also an electron and electron. These are still likely. Okay. But in the here in this process, let's say this becomes an not an electron. This becomes a mu1 somehow. That's a mu1. I don't know what I don't know. I'm just making stuff up here, but that's the idea. Some mu1 and this is another photon. Okay, so photon. So you see that this is less likely simply because it's more complicated. Okay, all right. So anyway, let's go back to how it relates to IB. Okay, the idea here now is that for Feynman diagrams, there you don't need to know each and every one of those interactions. You just need to know what the interactions could mean and then fit that to the problem you have. You will never be given a problem wherein you have to figure out everything from scratch. No. Okay, everything's given to you in the diagram and you must use that to determine what's happening. Okay, so okay, here's a really common example. This is beta decay. Okay, beta decay is again the emission, for those who are not aware, this is the emission of an electron from the nucleus. Okay, the idea here is that a neutron is unstable. Okay, what basically happens here, the neutron turns into a proton and in the process releases an electron. Okay, so this is the simple version. Okay, that's a simple version, right? Makes sense, everything. But here's the thing, but if we put this in a Feynman diagram, because remember we have these rules for Feynman diagrams, these rules again are based on how what we know about quantum mechanics. Okay, Feynman diagram for beta decay. Again, this is one of those things that you need to know. And I'm gonna say beta minus decay for now. Okay, right. So in this case, again, this is your neutron, and if we let's not draw it like that. Let's just put it in like this first. It turns into a proton and in the process releases an electron, right? Let's make a Feynman diagram out of this as is. So the Feynman diagram for this is the neutron. Again, this is the time. Let's put time there. Okay. This is the neutron. Let's label that neutron. It turns into a proton and an electron. What did we just break? We just broke which rule? This breaks rule 2. Okay. In other words, because of Feynman diagrams, we now know that this decay is not exactly what happens. This is the end product, but this is not exactly what happens. So not exact process. Okay. Now let's take a look now, and let's actually let's use the Feynman diagram stuff. Again, time is gonna be here. And let's start with the neutron first, right? We know that the neutron is a matter particle and that the proton is also a matter particle. So this works. But we know from a Feynman diagram that there must be something here. I'm just going to use the wiggly line again, right? So far, rules are not broken, right? But this means this wiggly line eventually must turn into an electron. But there is something amiss. If it's just like this, it still breaks one rule. It breaks rule 1. It still breaks rule 2, right? still breaks rule 2 as is. Which part? That part. Still breaks rule 2. Okay, so this is now, let's duplicate this to make this easier. This is now, we'll correct this. So we need to correct that. There has to be something going into it. Okay, so there are two ways to draw that in arrow. It's either this or this, right? Okay, for beta decay, we figured out, I'll just tell you this much now. In beta decay, we'd figure out basically that it's like that. Okay, and then, well, it's pointing to the left. So this must be some sort of antimatter particle, right? Okay. We now know that this is called the antineutrino. Okay. And yeah, this is how we figured out that beta decay is not as simple as it looks, just from the Feynman diagram. Okay, now the real thing we're going to look at here, and the final thing we're going to look at here, is, let's go back to quarks. Protons and neutrons, again, this is up, down, and down, right? So let's call that a down quark here. I'll put the down quark here as well, and then the up quark here. This has an up, down, up. So you see that, let's use green, okay, that this up quark doesn't really change. So there's no interaction, so we can just do it like that, no problem, because there's no interaction. Similarly here with this down quark, there's no interaction happening in this down quark, so it stays as is. But this down quark changes into an up quark, and that's the exact process in beta decay. Now what we figured out is we have discovered this particle. This is the W minus boson. Okay, and therefore, why is it W? This is W because we named it after the weak nuclear force. That's why it's W. Okay. In other words, the weak nuclear force, this is what you would always read in a textbook. The weak nuclear force is a little weird because gravity keeps, what are the four fundamental forces? Let's start with that. The four fundamental forces are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. The first three, they kind of like explain how stuff attract or repel each other. It's about forces. But the weak interaction is not a force in this sense. It's basically just an interaction that allows for beta decay to happen. Okay? But having the weak nuclear force also allows a lot of other stuff to happen in the subatomic world or in the particle world. Okay? So that is how you do Feynman diagrams. So again, I want to emphasize here, for IB at least, okay, emphasis for IB physics. Okay, again, you are not expected to know all possible Feynman diagrams. That's impossible. Okay, but you're expected to know, you are expected to do two things. First is know how to interpret Feynman diagrams. And the second one, and you are expected to know, I'll make this like this now. Oops. You're expected to know Feynman diagrams, and you're expected to know how beta decay happens. Know the Feynman diagram for beta decay. Whether it's beta plus or beta minus. Or beta minus. Okay, so with that, before we end, I'm going to just show you how beta minus looks like. Beta plus. Okay, so beta plus is a proton turns into a neutron. This is beta plus. Okay, the idea here again is we're gonna do time like this, and we're gonna go to the quark. So proton is up, up, down, and then a neutron is down, two downs and an up. So this is what I'll do. This down stays as is, nothing happens. This up stays as is, but this up must decay into a down. So we go Feynman diagram. That's gonna happen. We have our arrows coming in and arrow coming out. We must have a wiggly line, right? And this wiggly line must have an arrow coming in and an arrow coming out. Oops, that's 2 ins, so I broke a rule. That's it. Okay, and then in this case, because the up turns to down, this is now the W plus boson. Okay, and then what's produced? You have the anti-electron, also called the positron. Okay, and then you have the neutrino. So that's what's produced. So you have to memorize these two particular Feynman diagrams. But even so, I'll just emphasize the one thing, you're not expected to actually memorize these. So one thing that I would ask you to focus is what kind of boson is produced. Okay. So beta minus, it's W minus. Beta plus, it's W plus. It's as simple as that. The rest of it follows Feynman diagram rules. Okay, I think we'll end it here. So for those for my grade 12 students, if you're listening, thank you. Anyone else who's still listening, thank you for staying. So we'll end it here. Okay, so not quite yet. I think I'll stay for 5 minutes. Anyone with a question, you can put it in chat. If I don't get a question in a minute, that means we can end. Okay, so yeah, at this point, remember, grade 12, you're already familiar with these, so this should be more or less a review for you. But for those who are new to this particular idea, I just want to go back to this bit. Okay, not that one, this one. So a Feynman diagram is just a tool for you to see which possible interactions happen, and you must remember the 4 main rules. There are other rules, but for now, at least for the IB, these 4 rules are enough. Okay, so again, let's go through the rules. There must be junctions everywhere, unless there is no interaction. Okay, now an arrow in, there's an arrow out, and there's a non-arrow or a wiggly line. And then your rules, rule number 3 is that there must be a time arrow. Again, time arrow for IB is usually to the right, but be aware that there's a time arrow going to the going upwards. Okay, and finally, rule number 4: arrow in the same direction as time is matter. An arrow in the opposite direction of time is antimatter. Okay. Last thing before I go, since there are no questions, I'll just go to another particular thing. Okay, so this time I'm going to do let's do something with the strange quark. I'm gonna look for a particle with a strange quark. I'm just looking for the name, but I can basically let's see, this is Sun. Okay, let's do this one. Okay, let's do this. Let's say that you have strange and okay. Strange and okay. Strange and anti-down with okay. Kaon. Okay, let's go to this. Let's go to this one. Let's call the kaon. Okay, a kaon is composed of okay, specifically a neutral kaon. Okay, a neutral kaon would have a composition of a strange quark and an anti-down quark. Okay, if you're not familiar with these notations, yeah, I think I'll go through this notation some other time. But this means, let's go. This means this is a strange quark, and this is an anti-down quark. Okay, now the kaon. How does a kaon decay mode for kaon? Okay, there are just so many possible decay modes for the kaon, so I'll look for one particular kaon. Oh, apparently it's not the kaon, the strange anti-down. Okay, I'll change it. Okay, let's just make that the strange and that. Okay, so it's gonna be down and anti-strange. Okay, now this usually decays into okay, let's use this one. This decays into a let's look for an easy one for now. Hold on. Pion. Okay, so this usually decays into a pion. Okay. Into pion. Now a pion, this particular pion would be let's look for the decay. Okay. Let's say that this decays into a down anti-down. Okay, so down anti-down. Okay, there. So how would this look like in terms of the Feynman diagram? So again, 9 would be here. So we have the down and the strange anti-strange quark. The down stays down, but this down is now anti-down, right? So let's make a junction. Let's make our arrows and our wiggly line. So what happens here? Strange is antimatter, so it must point to the left. Down anti-down is also antimatter, so it must also point to the left. That still follows our rules of arrow in and arrow out and wiggly line. So we're okay. Then what's that wiggly line gonna be? This could I'm not sure what this is, but you know, I could guess that I'm gonna guess this is again a Z. This is a Z. This is also for weak, but this has no charge. Okay, why do I know it has no charge? Because the idea here, we'll get to that at a different lesson, but the idea here is strange quark is negative, positive rather, because it's that. A down quark is negative, this is negative, and this should be positive. So what comes out must have no charge as well, but that's for another time. And then this thing, this Z minus, will have to decay into something else again. Let's just say one going in, one going out. Usually this decays into an electron and an antineutrino. So antineutrino. There's a possible way to do it. There are other ways to do it. Like it could go antineutrino, or it could go neutrino, anti-electron. I know that doesn't work. It cannot be antineutrino here. Why? Because it has to be positively charged. This has to be electron, or the anti-electron, like that. Okay. All right. So we'll end it here, because I don't see any other questions. So we'll end it here. Anyone listening, thank you for listening. So before we go, of course, the usual, don't forget, subscribe, like, follow us on TikTok and Instagram. Thing is, I don't get a lot on Instagram. I usually, for shorts or for short format videos, I usually get it on TikTok or here on YouTube. So we're okay either way. Twitch is just, I'm okay with not too many followers in Twitch, but yep. I'm really mostly active on YouTube and Facebook and TikTok. Okay. So please follow us there. If you'd like to follow the other two, go ahead. So for now, we'll end it here. Have a good day, evening, good morning, wherever you are again, and stay freaky, everyone. Bye bye now.